Okay, well, once again, thanks for the introduction. And of course, let me thank Radu Jura, who I think has to teach right now, as far as I know, for the setting up of the seminar and also for the kind invitation. Needless to say that for an Austrian, it's always nice to cycle back to the capital. And yeah, I think it's a good opportunity also to meet many colleagues and friends. I'll talk about quasi-variational inequalities, which are not optimization problems per se, but of course our sort of tour started with variational inequalities, optimal control, and then quasi-variational inequalities, optimal control. In a sense, you first need to understand your state system to some extent before you can really control it, and this was why we got interested in quasi-variational inequalities from a methodological point of view. Also, I'll talk briefly about semismooth Newton methods because there's an interesting result telling us something about the semismoothness of a solution map of a variational inequality, which can be used in a beneficial way. I'll then say a few words about optimal control. When I sent the title, I think I was not aware of the length of the time slot, so I'm not sure whether I can touch uncertainties. But I think given the fact that this uncertainties is just justified because uncertain things may come or not. Let's see. So this is joint work with a number of colleagues in Berlin, like Amal Alphonse, Caroline Gersbach, Carlos Rautenberg, who moved to the US, Thomas Roviotz, he's in Norway, John Papadopoulos, he's a so-called Dirichlet postdoc in the Math Plus Excellence class, and Konstantin Christoph from the TU Munich. Now let me start with QVIs, and I'll write down here a variational inequality where K is a non-empty convex closed set, could be a cone, but doesn't need to be, and then a variational inequality involving some operator A, which I don't specify for the time being. Of course, looks like this. We would like to find an element in K such that this inequality has to hold true. And this inequality may come, of course, from a first-order optimality consideration for a minimization problem, or it may just come by its own right. And as I said, for some time we were interested in studying these problems, in particular numerically, because, well, we wanted to find a kind of mesh-independent solution method when it comes to differential operators, as it was mentioned up front. So the idea then is, of course, you would like to devise a method, ideally in function space, which after discretization then exhibits a discretization-independent convergence behavior in the sense that if you start on at the same starting point, regardless of the fineness of the mesh, you more or less get the same number of iterations to get close to, say, an epsilon optimal solution. And we did so by using Moreau-Yoshida regularization techniques, but of course then you embed it into some path following. You have to handle the path versus the discretization finite. We also did optimal control, and of course you immediately end up, so let's assume F is a control, Y is a state, then you end up with an MPEG, or maybe bilevel optimization problem, and then you have all these delicacies, as we know from MPEGs with constraint degeneracy. And then in function space, you find out that there are even new versions of stationarity which are really connected to the function space and which you do not see in finite dimensions. What's the difference to the QVI? In my understanding here, the QVI it looks more or less the same, except for the fact that the K may now also depend on the state. So you have a solution-dependent constraint set. And of course, one immediately realizes such an entity almost never comes from a first-order optimality condition for a minimization problem, but it stands for its own right. Of course, if you start to think iteratively and say, well, I'll fix the Y and then I solve a VI, I get the new update and so on, then you may say this is an iterative way of thinking about it, and then every iteration may be connected to an optimization problem. It's non-smooth because of the variation inequality nature. It's non-linear, well, for many reasons, as well the inequality, but also potentially in the K of Y. And it may not have single solutions. It could have set-valued solutions. Now, the reason why we got interested in QVI from an application point of view, I gave you some glimpses from the methodological point of view. I think there are several lines. One really was connected to a collaborative research center in biomedical applications, where the beating heart is in a kind of surrounding tissue, the pericardium, and you have inside the epicardium, and these two kind of tissues get into contact. But as you can imagine, it's a sort of compliant contact, because as the heart expands, it will push the outer obstacle in a sense, but it will be confined. There is no penetration, so you cannot get the inner material outside of the outer material. So you get the unilateral constraint in the K of y, but you have a constraint which is not rigid but depends on the state. The other application which interested us is completely different. If you have, let's say, some surface and you pour granular material on the surface, then depending on the material, you will have piles of materials being formed, or landscapes or rivers, depending on whatever is pouring down. And each material has a specific angle of repose, giving you specific structures. And depending on the underlying surface, you get interesting objects. And this, again, is a QVI, because if you pour something at some point, if the slope is too steep, then suddenly you have a state-dependent behavior and things are sliding down. And the third application comes from thermoforming, which is a kind of billion-dollar business where you have forms, typically plastic sheets, being pressed into molds. Molds, there could be some temperature, and under the temperature, the sort of mold or the obstacle gives in, and you have a compliant obstacle once again. And of course, you would like to maintain a certain shape, and this is where you would like to control this. I'll try to cover a bit on existence theory from three different perspectives, because they are sort of interesting, each of them in their own right, and I'll tell you why. One of the major issues, of course, is to understand stability, like Lipschitz behavior of solutions as functions on the data, for instance, f here. It's also interesting to understand sensitivity. If you think about deriving first-order optimality conditions for control problems, at some point you have to understand how does the mapping, for instance, f, if it would be the control onto the state y, work. And this is where we're interested in this. I'll talk about the Semismooth Newton part and optimal control, and let's see whether I can touch uncertainties, perhaps not, but if somebody wants to have the slide, I'm happy to share. Now, maybe I shouldn't be too technical here, but I'll start in potentially infinite dimensions. There's the L2 space as the pivot space, otherwise I have a Gelfand triple V. You can think of V being in Hilbert space. V star is the corresponding dual, meaning V embedded continues in L2, it continues in V star. Omega is some underlying domain. This is where the PDE later on, or the operator, will operate. And there's also another condition which is, for instance, typically satisfied if you have the Sobolev spaces W1R. Once differentiable only, so meaning that maxes and means or absolute values are in the same space of functions, which is not true if you crank up derivatives, because then, of course, if you take the max of a smooth function, it doesn't need to be anymore in a corresponding set. The operator should be linear, bounded, coercive. Constants later on will be CA, CB, and this is a T-monotonicity property involving the the negative and the positive part of the function, which, of course, if y as a function is taken in a pointwise almost everywhere fashion. There are many ways to look at constraints. I'll stick to what I called earlier the compliant obstacle. The classical obstacle problem would have a fixed upper bound, but here I allow later on that the k depends, as you have seen, on y, and this makes this a state-dependent upper bound. With a fixed upper bound, I'm falling back onto the VI context, otherwise the VI context. Okay, now this is written down the problem once again. I have some data assumptions now, but otherwise no surprises. Examples, I already gave you that, for instance, H01, which is like W12 with homogeneously theoretically boundary conditions, or trace 0 would be one space which would be suitable, but also fractional spaces S between 0 and 1, which give rise to non-local operators. Partial differential operators can be carried on as well here. For the phi, I'll need later on always some sort of complete continuity or compactness property, meaning that weakly convergent sequences will be mapped on strongly convergent sequences. And this is, for instance, satisfied if I hit the y by some solution operator, for instance, associated to a second order elliptic partial differential equation, because then I get a sort of compactness, and there are examples falling into such a framework. Let capital Q be the solution map, as I said, potentially set valued. This is why I see these double arrows here. And for the VI case, if I come back to the sensitivity aspect on the previous slide, there is work by Mignot in 76, so he has shown that there is a differential stability in a sense that you have directional differentiability of the solution map of the VI according, for instance, to the data F. And there was also a kind of affine variational inequality written down to characterize that solution. The QVIs, I think, case was open until I think we, together with Amal Alphonse and Carlos Rautenberg, looked at it in 2019. And we have some very recent paper with also including Gerd Wachsmuth, where we extend that framework. All those assumptions are satisfied for thermoforming, which I've written down here in more detail. Again, in a 1D schematic, you see here the mold. You see here, let's say, the boundary of some, or deflection of some, let's say, plastic sheet, which you push against the mold. Then you have an equation, which is here, theta is the temperature. There is a transfer between the two surfaces, depending on whether they are in touch or not. And this is why you see here this coincidence set. The characteristic function is 1 if u equals phi, which means they are in touch, otherwise it's 0. And then there is an equation regulating the deflection of the membrane away from some fixed equilibrium position, phi naught. And of course, the deflection of the membrane here, so this is the compliant obstacle, sorry, and the deflection of the membrane here has to satisfy this unilateral problem, again, meaning the red part cannot penetrate through the blue part, it always has to stay on one side, but the blue part may give in as the red part touches the blue part. This is what makes the constraint. Okay, now existence of solutions. One way to look at it is the Birkhoff-Tartar approach, where you have a mapping, call it T, or mapping T between two, from a Hilbert space into that very Hilbert space. If that mapping is increasing and you have that super and sub solutions are ordered in the appropriate way, then you can show that that mapping has a fixed point, or the set is a fixed point is non-empty and is within, let me call it, the interval of subsolution and super solutions. And that's what I'm using here. So if the mapping phi on top of what I had to have before is also increasing, and let's suppose we have this behavior that there exists sup and super solutions, where S is the solution map for this variational inequality, where I fix the argument here and otherwise also the F. Then if it's ordered, as I just said, the theory tells us solution set is non-empty and is within these two bounds. The reason why this is interesting is you now can order solutions, and you can, and again, solutions are functions possibly, and you have a minimal element and a maximal element. And that's kind of interesting because these can be very relevant quantities when you think about controls. Whenever you have a non-uniqueness in the solution set, you may think about designated solution. For instance, you may start to minimize the distance between the upper and the lower solution, or the maximum minimum solution, or involve those solutions in other ways. And for instance, if the data behave like this, examples for such minimal sub and super solutions are the ones which I'm highlighting here. So in that sense, we indeed have valid examples going into this. Secondly, iteration schemes. What I gave you in the introductions is something which has been used also as an analytical device to prove existence, where you say I have a kind of initial idea for the Y, and then I fix it, I fix the constraint set at that very Y, solve the variational inequality now, get a new estimate for this Y, let's call it Yn, and keep repeating this process. Then I may be able to show that that converges, and if it does so, I most likely will be able to show that there exists, that the limiting object is a solution of the quasi-variational inequality. And under these assumptions, remember I mentioned complete continuity already, and this or that assumption here where the constant here needs to be small enough. So this is again the coercivity and the boundedness of the operator A constants here. Then you have convergence of that sequence. Sorry, the n is should be a lower index here again. Converges from above against y. And the interesting aspect is if you start from a soup solution, you can even set up the scheme so that you converge from below against the soup solution, because the minimal solution, and the same is true for the maximal solution. So in that sense, it's not just a kind of Birkhoff-Data existence theory, but we can also make it sort of practical. Of course, I couldn't give you a speed of convergence result here, but at least there is an iterative mechanism which gives you the minimum and the maximal solution. What is also sort of traditional in the community, in particular when it comes to control, is that you regularize the problem. So you may think of M being some regularized max operator, so it's sort of smoothed around the kink. And then you're sort of penalizing deviations from the constraint here. There's a parameter rho, which you then have to drive to 0 in my setting. And then it turns out, again, under some assumptions, you can even think about a perturbation analysis here where the F could either be fixed or has some perturbation F rho going to F in V naught. Then you can prove that the corresponding solutions as the sequence rho n goes to 0 will also converge to solutions. The Birkhoff-Data approach is interesting because it allows us to order. We have minimal, maximal solutions which are useful. The iterative procedure is interesting because this is very often used as a sort of numerical device. It's not a very advanced technique, it's a sort of fixed point iteration, but nevertheless. And it gives us a mechanism to compute minimal and maximal solution. And finally, very often having a smooth problem here is useful when you think about control, because then you get rid of the degenerate constraint, replace it by a PDE, where you can use KKT theory and then pass to the limit. So in that sense, all of the three approaches are useful. Now what about directional differentiability? I think I have to be a bit quick now, but let me ask, I started when? Do you remember? 10 minutes, okay. This reminds me of a conference talk which at some point I attended. I think maybe some of you did it as well. I shouldn't use my time now in this way, but nevertheless. There was a fire alarm in the hotel. Everybody had to leave the lecture. We came back 10 minutes after the fire alarm, and then the chairman said, anyway, we have to stick to the schedule, and the poor person who had to talk 10 minutes less. So in that sense, you're very gentle here. Okay, and gladly no fire alarm. Okay, now what about directional differentiability? To make a long story short, you can prove directional differentiability. Again, Y is the solution set. There's a perturbation regarding F, because F is my control concept later on. So I'm picking a direction D, and I have some sort of scalar sequence S, which goes to 0, and then I look at such perturbations. Ys is the corresponding solution for the QVI. And then as S goes to 0, I can expand the solution in this way, where the alpha is perhaps a fancy notation, but it solves this quasi-variational inequality, which again characterizes the sensitivity. And the ky alpha, if you look at it carefully, it's more or less the sort of critical con you would expect to appear in this context of sensitivity. I mean, this is very compact. The paper is very long because there's a very delicate interplay of sequences. If you think about S going to 0 and other kinds of sequences being involved there, so you have to prove some uniformity at some point. You need to show that you can flip sequences, and that takes some careful analysis. Yeah, okay, I think that's what it is. You can also more or less do the same thing for the for the minimum maximal solution. So we also have a sensitivity result for these designated special solutions. Here I do not go into the details, but again, you can characterize it by some sensitivity alpha, which again has to solve a QVI in its own right, reminiscent of the one which you've seen before, but of course now involving the minimal solution, and there's an analogous result for the maximal solution. I think that's what this more or less tells us. And the Km is more or less a related critical count, but now instead of y, you have the minimal solution m, and you can do the same thing for the maximal solution. In our initial work, we had to constrain our perturbation directions to sort of non-negative elements. And in a very recent work, we could do the following. If the control or the data f is in some space which is contained in V star, and we have such a property here in the neighborhood of the data f here in W, and analogously for the super solution U bar, then it turns out we can remove this and look at perturbations d in the tangents cone regarding W at f. This gives us now more freedom, so to speak, to move directions, and this is something, of course, which is relevant. There's a very recent preprint in case you would like to see. Now, inexact and globalized semismooth Newton. Nothing fancy here, but perhaps sort of maybe interesting. What you can, of course, do, you can rewrite your QVI in terms of a fixed point equation. If you have a y, you take the phi operation, map it on phi of y, and then you solve the variational inequality with upper bound phi of y. And this is the sort of superposition of these two mappings here. And this should give you back the solution y here. So this is a fixed point equation. And if, of course, H is a Lipschitz contraction, well, then fixed points exist. So this is one aspect of it. Now, but we were interested in doing some sort of locally fast solvers of semismooth Newton type. Well, semismooth because apparently there's a non-smoothness because of the mapping S, potentially also because of phi, but phi could be smooth for the time being. But the solution map for the via will for sure be a non-smooth operation, unless you have strict complementarity at the solution. The algorithm would take as an input the residual R, some initial guess, some parameters, tau 0, tolerances, and sequences, tau I, rho I, giving us some flexibility in computing inexactness, and gives back a numerical solution, which I call y tilde star here. What it does is sort of simple. It checks whether tolerance is met. If yes, stop, fine. If not, you compute a fixed point update, so which means you just evaluate S after phi. But remember, phi may involve the solution of PDE. This was the L-1. S needs to solve a variational inequality, so the evaluation of H in its own self, in its own right, requires already some effort. And then you may say, I don't need to solve, sorry, the U should be a Y here. I don't need to solve it exactly, but just to some tau I tolerance in view of the previous residual. Simultaneously, you compute an approximation of the Newton step so that you, again, with respect to parameter rho I and the previous, it should be the residual, I guess. No, it should be H. No, it should be the residual here, sorry. And then you compute that one, again, inexactly only, and you check whether the Newton residual is better than the fixed point residual. If it is, you accept Newton. If it's not, you accept fixed point. That's a kind of simple globalization, of course. You may come up with other techniques, no doubt about this. But you get at least the following convergence results. If you think about the tolerance positive case, well, then you stop either immediately, of course, trivially, or trivially because the mapping is simple, because the Lipschitz constant is supposed to be 0 here, or after at an iteration index I, which is the next largest integer to this number here, which involves the logarithm of the tolerance, the residual, and some parameter lambda, which you can choose here. And if you check the interplay of lambda being close to gamma versus close to 1, of course, there's a kind of a balancing in the good and negative side. And the last iterate yi then satisfies the tolerance, of course, condition, and it's tol over 1 minus gamma close to the true solution. And if the tolerance is 0, well, then either you stop finitely or you get a locally superlinear convergent sequence. And the point is, sometimes fixed point iterations can be awfully fast. Normally they are not. If the fixed point iteration is not fast, then the result tells us at some point the Newton step will take over and you will inevitably have local fast convergence. And this can be analyzed. So this is what we did for the obstacle problem here. Again, specific operator here. This is reminiscent of the thermoforming, where you have a fixed position and some deflection of the mold, which comes from some thermal processes. You can transform this sort of away by a simple transformation and a solution map for the VI, where you don't have an obstacle, but this corresponding forcing term. A of phi is the active set, I of phi is the inactive set in sense of capacity theory. I don't go into the details, but it makes a difference for H1 functions, whether we talk about almost everywhere, quasi everywhere. And that's the issue related to capacity theory. And then you can characterize, but first of all, we know that S, the solution for the variational inequality, the map is in general only Hadamard directionally differentiable. And you can characterize this Hadamard derivative GS here with a specific choice, so that's what you get here. So the ZS is a sensitivity which, for instance, so this is the inactive set. You may think about in a pointwise setting on the inactive set, negative Laplace of this ZS equals G. But of course, here it's a bit more delicate because of the fact that the dual space is not interpretable pointwise. It's a sort of space of functionals. But this ZS comes in here, that's a true Laplace operator here, and this is the characterization of one of such derivatives which you may use. And then it turns out that the solution map for the variational inequality is Newton differentiable when endowed with this specific derivative. And then, of course, there's Semismooth Newton theory, which tells us that locally we'll have fast convergence in function space. And then Michael Ulrich and myself, we wrote the paper on mesh independence of that methods. And then you can also prove that there is mesh-independent convergence. Okay, so we did some results in thermoforming where we have an explicit solution. Where in one example we set it up so that there is a contraction as we needed it for capital H, and the other one there is no contraction. What you can see here are fixed point iterations in circles, blue and green, from two different initial points. Blue is just a zero, and green is the inverse Laplacian applied to F with homogeneous directly boundary conditions, and you can see here convergence. So it's a simple example in 1D. In that sense, even fixed point is sort of quick, but Newton is even quicker. This is what this tells us here. So this is the number of outer iterations. This should be Y's here, sorry for this. And you can see here the advantage of Newton methods. So this is for the example where we do have contraction. If you don't have contraction, the fixed point iteration runs into some trouble, and you can never accept for some reason the Newton step in this setting, and everything sort of stagnates. On the other hand, if you throw the fixed point iteration overboard and just to Newton, it turns out it converges nicely, but of course there is in principle, in general, no guarantee, and this is just the corresponding. I think I'd rather stop here. The next part would be optimal control. So we also derived some stationarity conditions for this control problem, but yet we need to define an algorithm to solve that. Maybe for a different one-world seminar in optimization. Thank you very much for your attention.